Welcome to today's lecture of QEEE on the topic earth pressure on retaining structures. We are continuing with this topic. Today is the last or third lecture on this topic. In the previous two lectures on this topic, we have covered the earth pressure theories and the design aspects for rigid retaining wall. And today we will start with flexible type retaining wall, and one of the flexible type retaining wall is none other than the sheet pile wall, where we have defined also the flexible retaining wall are those where the slenderness ratio is very high. That means height or length of the retaining wall is much more compared to its cross-sectional size. So if we look at the usefulness and sheet pile wall, what are those things? So essentially we can say that sheet pile retaining walls are usually used in kind of soft soil, and wherever there is a scarcity of space, so there we generally use for sheet pile wall. So it has both permanent use as well as for temporary use we consider the use of sheet pile wall. So sheet pile walls can be made of either steel or vinyl or wood planks, or which are driven into the ground. For a quick estimate of the material, how much it is required, usually driven is about 1/3 above the ground and 2/3 below the ground. It is not always true actually. It depends on how you are designing, depending on your soil condition at the site and many other things. So we will discuss those things in today's lecture. Now taller sheet pile walls will need a tie-back anchor. So we will explain that also very soon, or in other words it is called dead man, placed in the soil at a distance behind the face of the wall that ties this wall, and usually by a cable or a rod or anchor are placed behind the possible potential failure plane of the soil. So essentially if we now look at here that what are the different types of sheet pile wall. So we say that there are basically two types of sheet pile wall. One is called cantilever sheet pile wall, and the other one is called anchored sheet pile wall. Now cantilever sheet pile wall also can be of two different types, like 1A and 1B. If we say, like one is supporting lateral load, it can be concentrated load, line load, and another is supporting backfill soil. So if we try to draw these two, or rather I will say altogether three different types of this sheet pile wall, how they will look like. So essentially if I try to draw through line diagram, this is the example of 1A, that is cantilever sheet pile wall, which is supporting a lateral load like this. So where we get this kind of phenomenon or usage of sheet pile wall of such kind, generally in offshore or close to shoreline, we generally drive the sheet pile like this, and ships etc. we generally tie with them. So this is the lateral pull or lateral force which is acting on this, and this side you may have the ground surface here with some amount of water standing over here, or there may be the dry section also. So both way it is possible. So this is a type of cantilever sheet pile wall supporting the lateral load. The another type of cantilever sheet pile wall which is supporting the backfill soil, is none other than this type. So this side of the sheet pile wall, it is supporting this backfill soil, whereas the other side we are trying to maintain this level difference, and this is what another type of cantilever sheet pile wall, which is the category 1B we have written over here. And the anchored sheet pile wall is nothing but when we have a very tall sheet pile which needs to support a taller section like this. That means when you are planning for very high level difference between these 2 points, essentially the cantilever sheet pile wall will not be stable, or you will not arrive at economic section of the sheet pile wall. In that case, we need to provide some kind of anchoring to this. So this is called anchored sheet pile wall. So this is the example of this second one, that is anchored sheet pile wall, where this excessive unsupported length has been taken care of through a kind of support by providing this anchor in the soil. So these are the various types of sheet pile wall which we generally encounter at field. Now if we look here further, that what type of deflection we can expect on this type of wall, that is depending on their pattern of deflection. Let us draw it here itself. If this is subjected to a load of P, it has to move something like this. So it has to deflect because it is pushing this sheet pile wall. So it has to deflect like this, and there will be a point over here below the ground. About this point it has to rotate. It cannot rotate about this point for obvious reason, because if it rotates about this point, what type of earth pressures are getting generated at this location, if you can see over here. So this side we can say active state of earth pressure, this side passive state of earth pressure, because the wall in this location moving towards the backfill, hence this side is passive. So I have written, let us say PA, here it is active AC, because here the wall has moved away from the backfill. So net difference of active and passive force will act towards this direction. So this is, let us say, resultant force of PR. Now if we assume that this point is at this location, then these two forces will provide a couple, and that will not have any kind of equilibrium. Hence it cannot rotate about this point, but it has to rotate somewhere above this bottom of this sheet pile wall, and this is the location of the point of rotation. So based on this point of rotation, why it is important, all our earth pressure diagram or equivalent earth pressure diagram we have to draw depending on both the sides of active and passive consideration point of view. Whereas for this type of cantilever sheet pile wall, the deflection also will be of similar nature like this, and here also the same logic will apply, that you have a resultant force coming from this side and we have some active thrust from this side. So to make this force in equilibrium, we must have this point of rotation somewhere above the bottom of the sheet pile wall, so that there is also another resultant force of PR1, let us say, so which will make the system in equilibrium. So what essentially equilibrium we are looking at this kind of cantilever sheet pile wall problem, if you look at it carefully, essentially we have to satisfy the criteria of sum of all horizontal forces equals to 0. Now what about the sum of all vertical forces? Look at here, compared to those horizontal forces, the amount of vertical force which is acting is negligible, very negligible, because these sheet piles are thin sections. So you can as well neglect or consider that vertical equilibrium is well satisfied with respect to this and the tip reaction or the upward reaction coming at the bottom of this sheet pile wall. So that's why mostly we don't consider the vertical equilibrium as such, but we have to consider the horizontal equilibrium of all these forces. Next, we consider sum of moment about this, let us say about this point of rotation MO should be 0. So that by knowing these two, we can identify that at what depth this sheet pile wall D need to be penetrated in the ground so that the equilibrium or stability is ensured. So our basic criteria for design of sheet pile wall is nothing but to find out the value of this depth D and then apply some amount of factor of safety, let us say 20% extra or 30% extra. You can provide the depth so that the stability is ensured for cantilever sheet pile wall. Similar thing is applicable over here as well. The same concept, that is, you apply the equilibrium of all horizontal forces equals to 0 and then sum of moment equals to 0. For anchored sheet pile wall, if you look at this problem, then typically how it moves, it depends on what type of fixity condition you are considering at the bottom of this type of anchored sheet pile wall. Now, based on your assumption of your bottom support condition, there can be two possible ways of deflection like this, because if it deflects about this point in this fashion, it is quite obvious it has to be 0 here, the deflection. That's why this anchor has been provided. So anchor is having a pull out load here, let us say anchor load AP, and from this we have a resultant pressure coming from this side, which is, let us say, P resultant, that is difference of active and passive from both the sides, and this side also we have the active earth pressure acting from this side. So again here we have to maintain that sum of FH should be 0 and sum of moment, let us say about this point, the anchor location point say A, sum of moment about point A should be satisfied at 0. So by this we can solve for the anchored sheet pile wall, how much depth of embedment is required for this anchored sheet pile wall, as well as we can find out how much anchor load needs to be provided for getting the stability. But there can be another way of possibility of fixity of this anchored sheet pile wall, where the deflected shape will be something like this. This red color line which I have shown, that will happen only if this end point is acting as a fixed end. That means you have a sufficient embedment depth below the ground which provides a complete fixity at the bottom of this sheet pile wall, and because of that we call this way of solution is fixed earth support. Whereas the other one which I have shown earlier, that is called free earth support. So now if we look at the slide here, you can see here that for design of sheet pile wall, typically we follow the Indian Standard Code, Design Code IS 9527 Part 3. You can see that some portion of the code IS 9527 Part 3 is shown over here. So these are the two major types of sheet pile wall. I have already explained about that. That is cantilever sheet pile wall and anchored sheet pile wall. Now coming to that, how the pressure diagram or the forces acting for cantilever sheet pile wall. Let us now move to the solution part here. For example, let us say we are trying to find out what are the various earth pressures that are acting on cantilever sheet pile wall, which is embedded in cohesionless soil. So essentially, let us say in sandy type of soil, if we have a cantilever sheet pile wall, we can take any of the two types of cantilever sheet pile wall. Let us say here it is supporting the backfill soil like this, and let us say the necessary depth of level difference has to be maintained is H between the two sides of the ground. Now what is happening from the deflected shape? Let us now go back to the previous page and try to identify. Look at here. When the wall is deflecting like this, about some point of rotation over here, this side active earth pressure is acting on the wall because there is no lateral support here. Wall is moving away from the backfill, so this is active state of earth pressure. Now between this point, let us say point P dash, and this is, let us say, point O, and this is, let us say, point Q dash. So between point P dash and O, what are the pressures acting on this wall? Because both the sides now we have soil. So as the wall has deflected towards this side, so from this direction there will be passive pressure because wall has moved towards the backfill, and from this side there will be active earth pressure because wall has moved away from this backfill. So what is the PR? I said PR is the resultant of this passive minus active pressure, because we know for the same depth, for the same soil, passive pressure is of much higher value than the active pressure. And there is an assumption hidden in this analysis that full passive pressure is getting mobilized in this. Whereas below this point of rotation, that is between the length O to Q dash, what is happening? The deflected shape is this side. So now the wall has moved towards this side. So passive earth pressure is acting from this side of the soil and active earth pressure is acting from this side of the soil. So net resultant pressure again is passive minus active is acting from this side, because again passive has much higher value than the active one. So this is the resultant of passive minus active pressure between the length or between the depth O Q dash. So now understanding this deflected shape phenomenon, now we can draw easily what should be the earth pressure diagram behind this cantilever sheet pile wall. Let us try to draw that first. So first I am trying to show here what will be the net earth pressure diagram. So now based on the proposed deflected position, which is logical, I have explained already. This will be this form line, whatever is shown over here, that is nothing but the net earth pressure diagram. Now this net earth pressure diagram, now there are few salient points over here. This distance, let us say distance A, and from here to here, let us say this is the distance capital Y, and from here to here, let us say this distance is Z, and from this point to the point of application of this active earth pressure, let us say this is at a distance of Y bar. So is this clear? So essentially we have this net pressure diagram. If I try to draw it in this fashion, it is acting like this. So that is my net earth pressure distribution behind this cantilever sheet pile wall. Some of these parameters, let us say this value in the black, whatever I am showing over here, this is nothing but, let us say, small p suffix a. This value from here to here, let us say it is small pp bar, and this side, let us say this is small pp double bar. This distance is nothing but this y minus z. So y minus z is this much distance. What I can write now from this, that is pp bar is nothing but gamma of the soil, Kp minus Ka, that is passive earth pressure coefficient minus active earth pressure coefficient, times this height y. So that gives me the pressure at this base, because as I said, from this side we are taking the difference of passive and active earth pressure. That's what we did. Now at this location here also, if I want to draw from this upper portion, it will try to connect it over here. What I am trying to find out, what is the value of this intensity? This intensity now will be, let us say, pp prime. So this pp prime is nothing but, from this side I am now looking at gamma times h plus a times kp minus gamma times a, the distance this a, times Ka. Now what gamma we should consider? Always we have to consider appropriate gamma in the sense always effective value of gamma. If suppose if it is submerged, we have to take always gamma effective. And what should be the value of this small pp double bar, this one? This will be nothing but, here we have to make use of this pp prime. So this pp prime plus gamma times kp minus ka times y. You can see this is from the property of similarity of triangles. This one is nothing but you can compute in terms of this value. So that's what it has been done. Now how do we get the value of this distance A? That we will get from this value of intensity of PA. So if we try to write here A, small a, this distance is nothing but this small pp, small pa, this value, this one, this small pa divided by gamma times kp minus ka, that gives me this distance of A, because this side we have mentioned this is the resultant one, so it has to follow this one once you have the active pressure acting at this level as PA. So next, after obtaining all these values, what we will do, we will try to find out what is the resultant force. In this case, RA is nothing but, RA is, if we now give some nomenclature, let us say this point is A, this point is B, this point is C, this point as D, and this point as E, let us say. So RA is nothing but the area of A, let us say this is F, AFC. So RA is the force coming from the area AFC. So this pressure which I have shown over here, that can be easily obtained from this diagram. Now what about this pressure and this pressure? That means area of this zone and area of this zone. Next we have to find out, because we have to do finally the horizontal force equilibrium. So to do that, next what I can write, that sum of horizontal force equilibrium, if we write 0, will be nothing but RA plus small pp bar plus small pp double bar times z by 2 minus small pp bar into y by 2, that equals to 0. How we got this equation? Let us look back here. See, for horizontal force equilibrium, this force total we got. Now from this area we got, from this area we got. So RA plus this minus this will give me the sum of FH0. So that's what we did. RA. Now plus is this one. From here we are getting that PP bar plus PP double bar, this entire area, into Z by 2 minus what we did, this portion. That means PP bar into this Y by 2. So that gives you 0. Just from the geometry you can easily find it out. So once we get it, from here what we can solve for, here we will get Z. Z is nothing but given by, if you solve it, PP bar times Y minus 2 times RA by PP bar plus PP double bar. Now next, another equilibrium condition which we have to satisfy. So sum of moment equals to 0. Now if we take moment about the bottom of the sheet pile wall, that means about point E, what we will get? So RA force times this Y bar plus capital Y. Let us look it again here. See here, RA is acting at a height of, this is capital Y and this is small y bar. So RA times Y bar plus Y is the moment due to this force RA about base, plus Z by 3 times that PP bar plus PP double bar into Z by 2. That is nothing but, if we look back, this is the area. We have first taken entire thing in this direction. So it will act 1/3 from this base. So Z by 3 about this bottom, minus you have to take out this portion in this direction. So here it is Y by 3, that is 1/3 from this distance from base. So minus PP bar into Y by 2, that is the force, and point of application or lever arm is Y by 3, that equals to 0. Now substituting this value of Z in this equation, what one can get? One can get some solution which will be of the form of y to the power 4 plus y cube into some parameter, then y square into some parameter, minus y times some parameter minus some parameter equals to 0. That means essentially by solving these two equations, you will get an equation in function of y, and once you solve this, once you get the y, you get the known value of z also. What way it will help you? It will help you now to design this. If we say that this is the total depth of embedment, say df, so df is nothing but a plus y. So y we have now solved from that equation, and a we already know from these values, because pa you can easily calculate, gamma is known, kp, ka, all these values are known. So definitely this df you will get a design value of the embedment depth for this cantilever sheet pile wall, applying just force and moment equilibrium like this. And now if you want to apply factor of safety, so increase it by about 20%, 20% extra you put as df to this computed value. So that will be your design embedment depth for the stability of cantilever retaining wall. So that's what it is shown now in this picture. If you look at here in the slide now, what I have shown the solution. So this is only if you have water table correspondingly, as I said, the effective gamma always you have to take, because this is the earth pressure solution, only the earth pressure related gamma and kp, all these things you have to use. And this is the net pressure diagram which I have already shown, and using that you have to find out what is the embedment depth of cantilever sheet pile wall. Now cantilever sheet pile wall, this is in cohesionless soil what I have shown you. What will happen if we have a cantilever sheet pile wall, let us see, in cohesive soil. Now we will design cantilever sheet pile wall embedment depth in cohesive soil. So how we do that? So if I take the similar example of the cantilever sheet pile wall which is supporting backfill, here this side below dredge line you have soil over here, and level difference or height difference you are supposed to maintain, let us say h. So how to get this embedment depth here, this embedment depth? So this depth d we are planning to find out. Let us see what type of distribution of earth pressure will occur. Generally the earth pressure, if it is a cohesive soil, what will happen? For this side we have some distribution of earth pressure from this, you have this side some distribution, and it rotates about some point, and this one. So here the net pressure distribution will be something like this. You have here also, let us say PA. This point, let us say point A. This point, let us say point B. And this distance where this changeover will occur, let us say depth Z. Now how much the value of this one and how much is the value of this one, let us try to find out. So now from whatever earth pressure etc. acting up to this level we can consider it as a surcharge. So this we can say equal to the surcharge of Q. Now below the dredge line the effective pressure Q, but at point A what happens? Let us see. So at point A, if we say to the left side of point A, what is the surcharge? At this side of point A is 0 because this is the upper boundary of the dredge line. Whereas to the right side of this point A, what we get? This Q is nothing but your this PA, whatever you get from this upper layer, which is nothing but, let us say, Ka gamma H. So we are considering below this line it is a cohesive soil, and here it is we have taken as cohesionless soil or C5 soil. Accordingly you will get the value. So I am considering only the cohesionless soil. Now if I consider this as also cohesive soil instead of cohesionless soil, then Ka becomes 1 because for phi equals to 0 we already know as per Rankine's theory K equals to 1. So Q or PA becomes gamma H if here also you are replacing it and considering that throughout we have cohesive soil. So in that case the net pressure at point A, what it becomes? Left side this, right side this. So we can write that sigma P, that is passive pressure minus active pressure, the difference of these two at point A should be passive pressure. What it should be? It should be 2C because cohesive soil, minus what should be active pressure? Q minus 2C. So which gives us the value as 4C minus Q. How we got this value? Let us relook at it once again. So I am telling this magnitude is nothing but 4C minus Q. How we got it? To the left side of A here, sigma P. How much is that? Because wall is rotating about this side. So this side we will have passive condition. So that's why we are taking passive case. Passive case equation is Q times Kp plus 2C times root over Kp. Now for phi equals to 0 degree, this Kp also equals to 1. And what is the value of Q here? We have seen Q is 0 here. So this term vanishes. So this sigma P becomes 2C. That's why I could use it here 2C. Clear? Whereas to the right side, how we have written this one? This will be here to the right side, that sigma A is nothing but Q times Ka, that's what we did here, minus 2C times root Ka if it is a cohesive soil. So in case of cohesionless soil, first I have written this, but if cohesive soil is present, you have this one. Now Ka is 1 that we have seen because phi equals to 0 degree. So this becomes Q minus 2C. So that's why we have written here sigma A is Q minus 2C. So for this point A, which has moved this side, so this side passive pressure, this side active pressure, the resultant of the pressure passive minus active comes out to be 4C minus Q. Now if we want to see what is the net pressure here at point B in the similar fashion, what we can write at point B, let us see again, once again, it has rotated like this. So from this side we will have passive, this side we will have active. So we have to find out on the right side how much is the passive earth pressure equation, and this side we have to see how much is the active earth pressure equation. So if we now write down that at point B, this to right side of point B, sigma P is acting, which is nothing but Q plus, now gamma times D has got added to this, plus 2C, because here Kp equals to 1. Gamma D got added because here you have considered surcharge Q. Now surcharge has got added gamma times of this depth, so this also has to be taken care of. So Q plus gamma D times Kp, which is 1, plus 2C root over Kp, which is also Kp being 1, comes out to be 2C. And to left side, what is acting? Active earth pressure is acting, sigma A. So how much is the sigma A? Again, left side you remember what is acting over here. At this level there is no Q. So Q was 0, you can see over here. But at point B there is a surcharge of gamma D. So gamma D times Ka will work. So gamma D Ka minus 2C root Ka. Now Ka is also 1, therefore sigma A becomes gamma D minus 2C. Therefore net pressure at point B is nothing but sigma P minus sigma A, which is Q plus gamma D plus 2C, then minus of gamma D minus 2C. So that gives us 4C plus Q as the value. So if I go back here, so this intensity I got 4C plus Q. So this is what the pressures are acting. On the sheet pile wall. Now rest of the thing are similar to what we did previously, that you find out finally sum of Fh equals to 0 and sum of moment of all these forces are equals to 0. So this case generally we define that the number C by Q ratio is the stability number. So for 4C minus Q being 0, what we will get? The ratio of C by Q is coming 1 by 4. For stability, we should always check that this value of 4C minus Q must be greater than 0 for stability. Let us go back here, try to physically understand. This 4C minus Q must be present here. If this value is 0, then there is no support from this side, but you have pressure from this side, which is absurd, like it is not a stable condition of the wall. So for maintaining the stability, you must have this 4C minus Q non-zero or positive value. That's why this is the minimum criteria for cantilever retaining wall in cohesive soil to maintain this condition of 4C minus Q greater than 0. So by this process, using the sum of Fh equals to 0 and sum of M equals to 0, one can easily find out this embedment depth dF is required or D is required, and then increase it by about 20% as factor of safety. That is one way of doing it. Another way of doing it, instead of using C over here, you can use C mobilized. That is, C mobilized is nothing but the value of cohesion divided by the factor of safety. You use proper factor of safety of say 1.5 or 2 and then apply this condition that 4 cm minus q must be equals to 0, and accordingly greater than equals to 0 can give you the stability. So with this, now we have completed all the cantilever sheet pile wall. Now we will move to anchored sheet pile wall. So for anchored sheet pile wall design, how we do all the analysis, let us first try to understand. Let us first consider that cohesionless soil only, because if we understand the mechanics behind any type of soil, we can extend it for other type of soil as well. Now I was telling, for anchored sheet pile wall, we have possibility of two different types of fixity. One is called fixed earth support, another is called free earth support. So let us say the first one we are considering is free earth support system. So these names, free earth or fixed earth, came from what type of fixity we are considering and what type of deflected shape we are considering to form in the anchored sheet pile wall. Now this is our point of location of anchor plate. This is the dredge line, and rotation of this sheet pile wall we are showing here, the exaggerated version is this one. So it is rotating about this point. Here it has to be 0 because anchor you have provided. So this type of support at the end of the sheet pile wall is known as free earth support. And the distance, this distance where the anchor has to be provided is typically about 1 to 1.5 meter approximately from the ground surface. This is typical anyway, you can design for it. So what will be the corresponding earth pressure diagram for this anchored sheet pile wall? Let us now try to find it out based on its deflected shape. So at this point we have anchor pull out force here AP, let us say, and below dredge line this portion we have this side passive earth pressure, this side active earth pressure. So essentially net resultant pressure is passive minus active, whereas here we have active earth pressure only. So we can draw the net earth pressure diagram like this, where we have this value of RA, let us say this intensity is PA, and this value is, let us say, RP, which is resultant of the active and passive. What will be this intensity of pressure? That is nothing but, if suppose this distance is x, gamma times Kp minus Ka times x. And what is this entire embedment depth we are considering here? Let us say D. This point, this distance is small a, let us say, and from here to here, this distance let us consider as y dash. This is the height of level difference h, and from here to here, let us say this is h3. Okay, now what way we are going to solve this one? Again, it is very easy. Like A will be equals to this distance A, the small one. So earth pressures are acting in this direction. Let me show the intensity over here, and this side in this direction. So A is essentially the small pa by gamma times Kp minus Ka. Okay, so that we can see here, because here you have to find out the net of passive and active earth pressure. And how much is this distance y dash? This y dash is nothing but this h3 plus a plus this distance 2/3 of x. Now what are the unknowns in this case? Let us see. What do we don't know? Unknowns are like x we don't know, and how much is this anchor pull out AP, that force we don't know. So these two are unknown. And what are the equations we will get? Two equations we will get: sum of FH equals to 0 and sum of moment about this point A is equals to 0. See, if we do this moment equilibrium first, then this unknown AP will not come into picture. Other forces are known, RP is known, RA is known, only unknown is your X. X can be obtained by using this equation. Once you obtain using this equation the value of X, then when we do the sum of FH equals to 0, this is RP is known, RA is known, only AP is unknown, one can get the value of AP. So that is the way we can get easily the anchor pull out load or capacity which is required to be designed, and also the embedment depth D we will get, because A we know, X we have computed, so D is nothing but equals to A plus X, and then apply the additional factor of safety, so 20% extra you provide for D to get the design value of embedment depth for this anchored sheet pile wall. So this is the case for free earth support, how you can calculate the anchor capacity as well as the embedment depth. Now what happens if it is the other type, that is free earth support? Let us take the next type of anchored sheet pile wall. So based on the condition of bottom fixity, so fixed earth support. So for the case of fixed earth support, what we get essentially, let me draw here first a section of sheet pile wall which is anchored at this depth. So this AP. Now this is dredge line. As the name suggests, at the bottom of this sheet pile wall, the fixity condition should arrive. So there should be no deflection here, then it should deflect over here, there should be a point of inflection over here, and then finally it goes like this. So here there is, look at here at the bottom, unlike your free earth support condition, here is no displacement or movement as such. Now this point, how we are going to find it out? Let us mention some locations over here. Let us say this is point N and this is our end point C. If we try to draw the equivalent earth pressure which is acting on this system, typically it will look something like this, then this, then this, and this. Okay. So this is essentially where our point N comes into picture, and this is our point C. And this distance is like earlier we are considering A, and this is your PP, PA. You have of course your anchor over here, AP. Now this complete depth we are going to find it out at the end, and this point is point of inflection. Let us say this is point of inflection. That means here moment is 0. That's what it means, as we know. Now, how the bending moment diagram will typically look like for this case? Let us try to observe or find out. So this is C. Here is our dredge line. Here is our anchor location AP. Bending moment diagram will look something like this. This is point N. This point is X, let us say, and this distance, let us say, this is Y distance. So usually this point of inflection X, where bending moment is 0, is less than A, but need not be always. It can be above also, but most of the time it is so. So what we can consider here, we take this diagram, bending moment diagram, as we do for the beam. So we will take a fixed support with a prop, which is nothing but anchor location. So if you try to correlate, this is similar to something like this, what we know about bending moment diagram of this kind of beam. Now one can idealize it or assume it something like this. Instead of this fixed end, that is, instead of going up to the point C, you stop somewhere here, which is your point N, and consider the support here, such that your moment diagram is something like this, which is nothing but we are trying to impose here. So how one can make use of these things? So essentially what we get forces here. Let us say this is RB dash. This distance is, say, Y minus X. This is RB. This is our point N. This distance is A minus X. And this value will be gamma times Kp minus Ka times Y minus A. And the upper portion of the pressure diagram will be something like this, where you have this value as Pa, this distance is X, and here you have RB dash. So essentially what we are trying to say, that apply this load or this pressure on your beam and then solve it as a support condition like this actually, but idealize it like this so that you can find out the bending moment, etc. So using this, what we should do, we should design for the value of Y by considering the equilibrium of force and moment, and then finally provide the embedment depth D as 20% extra of that. So in this fashion, the fixed earth support condition also can be designed. But remember two things over here. For free earth support, what we got generally, D is lesser. I am telling all relatively, but section required is larger, whereas for fixed earth support type design, the embedment depth is higher or larger, whereas section required is smaller. That means both the methods have its own merit as well as demerit. So when you are going for actual practical design of this anchored sheet pile wall, one should check both the conditions of free and fixed earth depending on soil type, and then try to optimize which one will be most cost effective, whether fixed earth type or free earth type, because in one case you need more embedment depth, that means length is required is more. In another case you need cross-sectional area and sectional properties required larger. So if we now look at the slide here, so anchored sheet pile wall I was trying to describe. So anchored sheet pile walls are held above the driven depth of the anchors provided at a suitable level, and the anchors provide forces for the stability of the sheet pile wall in addition to the lateral earth pressure resistance, passive resistance on the other side. And it includes an anchor or tieback at or near the head of the wall or top of the wall. That's what I said, about typically 1 to 1.5 meter the depth of anchor we generally provide. One can use more than one set of anchors also if it is required. From the design criteria you can find out how much anchor load is required to maintain stability, because as I said, compared to cantilever sheet pile wall, anchored sheet pile wall are designed in such a way that they can maintain a higher level difference than cantilever sheet pile wall. So this is what we have already mentioned, a sheet pile wall which is anchored here. This is generally called tendon or rod. You can have different inclination and different types of anchors also, like you can see over here, different types. Even the inclined anchors also one can design. And as I have discussed in detail, there are two ways to design this anchored sheet pile wall. One is free earth support condition, another is fixed earth support condition. And in free earth support, this is the pressure diagram. We have already seen this, and this is finally what will act, and based on that you have to find out this embedment depth and this anchor pull out load. Whereas for fixed earth support condition, you have a fixity at the bottom. So from the pressure diagram, equivalent pressure diagram we put up to this point, and beyond that we generally extrapolate or increase about 20% more from that value of y, what I have said, and then provide the value of d. So this is also recommended in our IS code as mentioned over here. So if we try to compare between these two methods, I have already given their comparison major points for the comparison. It is listed over here. The free earth support method gives a pressure distribution that would apply when the wall is on the point of failure by rotation about the anchor point. That's why we are considering that equilibrium of moment about the anchor rotation point. But for the fixed earth support, it is unlikely to represent the true loading at any point of stage, because we are assuming and putting an equivalent amount of lateral load on this beam and then applying the beam theory for the solution of this sheet pile wall. So both the methods tend to overestimate the bending moment in the pile. The free earth support method is much simpler, that we have seen, because it is just equilibrium of two equations you have to provide, whereas for fixed earth support you have to truncate it from the bending moment diagram, and then from that you have to find out the distance and accordingly the earth pressure you have to take on the beam, and then you have to analyze that beam as per those earth pressure. So in the fixed earth support, depth provided is always more, because otherwise the fixity condition will not generate. That is the criteria, and that's why we have designed and seen the analysis. So moment throughout the section reduces because of that excessive or larger depth of the sheet pile wall. So a thinner section will be sufficient enough, but you need a taller or sheet pile wall or the longer sheet pile wall. Whereas in the case of free earth support, depth provided is less, but the moment coming to the section is comparatively higher than the fixed earth support. So a thicker section or a larger section for the case of free earth support is necessary for sheet pile wall design. So this is how the free earth support condition, we have mentioned the different sides, what active side and passive side, etc. And accordingly we have seen how this net pressure diagram acting for the case of cohesionless soil in case of free earth support condition. And then we have applied this equilibrium condition. This is the force equilibrium, and from moment equilibrium we get the distance. So this is the moment equilibrium from where we get the distance, and then finally we solve for it to get the value of embedment depth for the sheet pile as well as the anchor tension or anchor load, that is how much load anchor has to support. Whereas for the case of cohesive soil, the principle is similar as we have done for cantilever sheet pile wall. The same way we have to find out the net pressure at the dredge line level, both coming from left side and right side, to get the resultant of passive minus active earth pressure, that is net pressure, and accordingly we have to find out. So distribution here also typically will look like something like this, and here as well you have two unknown, this embedment depth as well as you have unknown of this T or anchor pull out load, and you have two equations available, that is sum of a horizontal load FH0 and sum of moment about this point equals to 0 will give you those two unknown. So that is how it is obtained over here. The same thing is mentioned in this slide as well. And this criteria we have seen that for stability this 4C by minus Q has to be maintained as a stability number greater than 0. So what are the values of factor of safety which is mentioned in IS code? You can see over here. It says that in designing cantilever pile wall and anchored sheet pile wall using free earth support, that is a factor of safety of 2 may be adopted on calculated passive resistance of the soil in normal condition, and one can adopt a factor of safety of 1.5 when earthquake forces are also considered in the design, because you have taken the extreme loading condition also. That's why lower factor of safety. In the fixed earth support analysis, anchored sheet pile wall, there is hardly any danger of failure due to inadequate passive pressure because you are going much deeper in the soil. So however, the computed depth of penetration, whatever we get from that analysis, that has to be increased by 20% to ensure that the fixed dead condition or fixity condition is arising at the site. Start another subtopic on this earth pressure on retaining structure, that is nothing but bracing system. So what is essentially this bracing system means? Let us first see. Like when we have to go for deep excavation or deep cut, essentially the shallow cut and deep cut typically is mentioned about 6 meter up to 6 meter depth. We mention it as shallow cut, and beyond that we generally refer as deep cut or deep excavation. Now when we go for this deep excavation, then vertical side with vertical side, if we are going for deep excavation, then it requires the lateral support to prevent the cave-in of the earth and to protect the adjacent area where other buildings also may exist, and due to the lateral movement of the subsoil. Now when excavations are shallow and ample or sufficient amount of space is available, then this is not required. You can provide a slope, flat slope, which will take care of these issues of excavation. But in deep excavation, especially in built up areas or urban areas where there is no available space, so you have to provide some kind of temporary earth retaining support system, which altogether is known as bracing system. That we will now see what is that bracing system. So excavations which are laterally supported, suppose this is our natural ground level, now it is required to make a deep excavation like this in the ground vertically, because here other structures are existing. So what we should do, we should construct some kind of lateral support system or retaining earth system with some lateral support system provided like this, which altogether the system will known as bracing system. So what are the various component of bracing system? Let us look one by one. So the vertical side of the excavations are supported by the sheeting and bracing system. So it consists of relatively flexible type of sheet pile wall or diaphragm wall. So essentially what we have learned, the sheet pile wall, so those things, or you can use the diaphragm, a similar mechanism or similar theory or similar mechanics you can apply. Now what will happen if you provide the diaphragm wall without any kind of support? It will try to get deflected like this, because as you go higher and higher in the elevation or towards the depth, the earth pressure will increase, because deeper the depth, pressure intensity increases. So it will try to come inside and finally it will collapse. So to avoid that, you provide some kind of lateral support at certain distances over here like this, as shown in this picture, which are known as struts. So these struts are nothing but horizontal members which are in compression. So what are the various uses of this braced excavation? Suppose if somebody wants to lay the underground pipeline, or construction of bridge abutment, or construction of basement, on underground metro railway construction, underground tunnel construction, or during any kind of temporary underground construction where this deep excavation is required, there these bracing systems are necessary. So what are the various components of bracing system? Now let us look at it. So in this method, the vertical timber sheeting, which are consisting of planks of about 8 to 10 centimeter thick, are driven around the boundary of the proposed excavation. So these are the timber sheeting or plank. In the olden days, that what it used to be. Nowadays for diaphragm wall we use the concrete wall obviously, or you can use the sheet pile wall also, the cast iron or the steel sections. The subsoil below this sheet pile wall is getting now excavated, and the sheet pile wall is held in its proper place by providing this strut we have seen. And another thing is mentioned over here, which is called as wells. So what is wells? Wells is nothing but another name is called also runner beam. That is the beam which connects from one end of this sheet pile wall or the diaphragm wall to the other end. So it goes perpendicular to this surface. So it runs in this direction perpendicular to this surface, that is called wells or runner beam, that provides support from the horizontal side if we look at the plan. So essentially, if I want to show you in plan how this bracing system will look like, so I am drawing the plan view first for the bracing system, and the same bracing system, now let me draw the sectional view. So this is plan, and this side I am drawing now section. So this is a sectional view. These are called, as I said, struts. This and this are known as diaphragm wall. or sheet pile wall, that is flexible type of wall. This one here is called wells, or it is also called, as I was mentioning, runner beam. So in this case, these are nothing but our struts in plan. From the plan view, from top view, we can see this is your boundary of that wells or runner beam, and this is your sheet pile wall. So if I put different colors over here so that it is easy to understand, this red color zone is my sheet pile wall or the diaphragm wall section. I have strut here, and this small portion which is protruded here, this side and this side, that I can see as this one, which is a small portion of this wells or runner beam. And the struts are placed at some interval which we call them as horizontal spacing or spacing in the plan direction, and here we call the spacing of the strut as vertical direction SV. So this is the vertical spacing of struts, this is the horizontal spacing of the strut. So this is how a bracing system will look like. Now let us come back to this slide again. So this is what is shown in this picture here: wells, struts and diaphragm wall or sheet pile wall. This is the section of the sheet pile you can see over here. Now how to compute the lateral earth pressure on this type of sheet pile or diaphragm wall? Because if you look carefully, you are providing some kind of lateral restraint or support to this. That means you are not fully allowing it to freely move. That means full active state may not generate. So it will be something not complete known theoretical earth pressure, but it will be something which is termed by Terzaghi and Peck as apparent earth pressure. That is not real earth pressure but apparent earth pressure. That is the terminology which was developed by Terzaghi and Peck initially, and later on Peck has defined. So it is called apparent earth pressure diagram, which is acting on the support. So what is that apparent earth pressure? Initially that Terzaghi and Peck both has mentioned that apparent pressure is about 0.65 gamma HK. So from various experimental studies, finally Terzaghi and Peck recommended in 1948, and later on Peck has revised it further in 1969, that this is the apparent earth pressure which is acting on this sheet pile wall or diaphragm wall. So this is what they have mentioned: apparent earth pressure diagram, 0.65 times gamma H Ka of Rankine for the case of sand. But if it is a clay, they said that apparent earth pressure will have different shape like this depending on whether it is a stiff clay like this or it is a soft or medium clay. So for that also they mention how we can define this soft and stiff clay criteria is that depending on what is your depth of vertical excavation H, gamma H by Cu, that is undrained cohesion, should be equals to 4. That will mention it is the condition in the stiff clay, and from the soil properties also you can get. Then the active earth pressure or apparent earth pressure, I will say, that is the more correct terminology. So sigma A, this suffix A denotes here apparent earth pressure. It will have this kind of trapezoidal distribution with 0.25 H up to this distance, then 0.5 H and again 0.25 H with an intensity maximum of sigma A apparent, which varies again between 0.2 times gamma H to 0.4 times gamma H. Whereas if it is a soft to medium clay, which will be observed or calculated based on the gamma h by Cu value greater than 4, in that case this distribution is here 0.25h up to this depth, then it remains constant up to 0.75h, this complete depth, and that intensity of apparent earth pressure is calculated as gamma h times 1 minus 4 Cu by gamma h. So in this connection, Peck mentioned that the stability number can be called as gamma h by Cu for the excavation in clayey soil, and that is how they mentioned initially that gamma h by C less than equals to 0 will give the earth pressure of value of between 0.2 to 0.4 h. So average value of 0.3 may be taken, and for gamma h by C greater than 4, the value has to be taken like this as shown in the previous figure we have discussed. Now how this design of strut should take place? So you can see later on the Tarzeghi and Peck's proposal for sand, that is 0.65h, that also they mentioned for dense sand and loose sand the different types of distribution to be taken care, and that distribution is for dense sand, it is a trapezoidal pressure distribution with 0.2h, then 0.6h, then 0.2h, whereas for loose sand it is 0.2h and then 0.8h. Whereas for soft clay and medium clay there is no further revision made by Peck. Now once somebody calculates, and what is that intensity for the sand, later on Peck mentioned that instead of taking 0.65h of uniform throughout, if we consider like this, you can take 0.8 times KAH when you are taking this kind of distribution depending on our dense type of sand. Now on the diaphragm wall or the sheet pile wall which is supporting here, how much pressure or earth pressure is coming is apparent earth pressure. Now depending on that trapezoidal distribution of earth pressure or apparent pressure by Tarzeghi Peck and later on modified by Peck, this can be a typical distribution we can say, and based on that typical distribution you have to find out the cross section of the diaphragm wall which will be suitable or stable, and accordingly you need to design. Then how you will design this struts, which are nothing but as a compression member it has to be designed, and this is like a small column you are designing compression member. This strut, how much load it is taking, it is nothing but the load which is coming from the surrounding earth. And how much load is distributed, it is assumed that each strut influence zone is 50% on the other side and this side from the ground surface complete distance. That means for strut 1, the pressure distribution you should take from the ground surface up to another distance which is SV by 2. That means this distance SV by 2 you have to take, and that will be influence zone or the pressure which you have to take for this area to get the total load which is acting on strut 1, and accordingly you have to design strut 1 as a compression member. For strut 2, again on this side SV by 2 and this side SV by 2, that will be the influence zone for strut 2, and this area total load whatever is coming, that compression load you have to apply for strut 2 and accordingly you have to design. Similarly for strut 3, SV by 2 in this direction, and the other side, suppose this is the last start and after that your ground surface is there, that is bottom of excavation soil portion is there, then take up to 50% of this distance, because it can be mentioned that remaining 50% load will be directly taken by the soil. So its influence zone will be this side and this side, whatever your free zone is there, half of that will give you the influence zone for calculation of load on strut 3. Now this diaphragm wall spacing etc. is mentioned over here. Typically this horizontal and vertical spacing we try to keep of the order of about 3 to 4 meter spacing. And how the diaphragm wall needs to be designed, you see, once we finalize depending on type of soil what type of apparent earth pressure will work on the side face of this diaphragm wall or sheet pile wall, now you can design it as a beam. And how you will design it as a beam, this is the load intensity which is acting on your diaphragm wall, that is the vertical diaphragm wall, just we have rotated 90 degree and take it as a beam, and this diaphragm wall getting support like this at various struts. So these are the three struts were shown: P1 strut 1, P2 strut 2, P3 strut 3. These loads are nothing but we have computed from that influence zone area, and the spacing between the struts is here SV. So if we take this SV as equals to L, so for this kind of multiple simply supported beam, we can find out the maximum bending moment will be mentioned as WL square by 10, where W is the maximum intensity over here. So you can grossly design the diaphragm wall considering the maximum value of W or pressure, earth pressure coming from this intensity, and L, whatever the spacing, vertical spacing of your struts you have, that square by 10 will give you the maximum moment. And once you know the maximum moment, now you can find out the sectional properties or Z to provide the diaphragm wall section. Now how to design the wells or runner beam? For the wells or runner beam, now this is the plan view. You can see this is the SH, that is the horizontal spacing of the two struts, and between this side we have wells or runner beam. Now on this runner beam, what load is acting at any level depending on at what level of ground you are considering. So at this level on runner beam only this much load is or intensity is acting, whereas at this portion on runner beam this load or this full intensity is acting. So generally we design for the maximum value. If you take the maximum value of this over here, so that will give you the W or P, and accordingly it is a simple supported beam because you get two strut location support over here with a distance of SH, this lateral distance. So for this kind of simply supported beam, we know what is the maximum bending moment. It is nothing but your load intensity is P coming from the maximum value of earth pressure intensity times your SV will give you the maximum load coming on an influence zone times your SH square by 8. So essentially WL square by 8 give you the maximum moment which is acting on this well or runner beam. Now this braced cut, if it goes through the non-uniform soil, how to analyze? It is quite possible that it may go through, because it is a deep excavation we are talking about, it may go through several different types of soil layers. So in that case, if you have various properties, so let us say H1 is a first layer thickness with properties gamma 1 and C1 for a clay, then another clay layer with H2 with properties gamma 2, C2 and so on. Then for braced design or excavation design, you can consider the equivalent cohesion and equivalent unit weight by just using the concept of weighted average of each layer, and equivalent cohesion can be computed like this, equivalent unit weight also can be computed like this, and then you can further follow the earth pressure distribution. That means apparent earth pressure distribution. In that you need gamma, H, C value, all those things. So it is shown over here. Suppose now if it is passing through layers of sand and clay, in that case equivalent cohesion and equivalent unit weight you also calculate using the same concept of weighted average of the properties of various soil. Now, what are the stability aspects one should consider for this kind of braced excavation or braced cut? The first criteria of stability is known as bottom heave. What is this bottom heave? Let us look. Once you make this excavation, deep excavation, what you did, you have taken out the soil from here. So the pressure got released from here. So bottom portion of the excavated portion will try to heave up, because this side you have your normal pressure whatever was acting earlier from the ground surface. So at this depth you have some kind of surcharge, and that surcharge will try to push the soil in this direction, and here will be possible soil will come out or bulge out. That is nothing but in the excavation pit you will find some heaving has occurred, which is known as bottom heave. So we have to find out the stability with respect, because if bottom heave occurs, finally everything will collapse from this side. So to take care of that issue, it is nothing but the principle of the bearing capacity failure can be considered as if some uniformly distributed load is acting from this side. This side also it is a symmetric view. So there is a failure zone followed by a Rankine passive zone and log spiral zone as per the Terzaghi's solution, you can always assume. And then that area, how much distance it should follow or how much zone it will completely take if it fails like that. That is, if that heave is occurring. You can see over here, suppose various layers of soil are here. The various clay layers are shown over here, layer 1, layer 2, layer 3. And layer 3 is the layer, suppose, where you decided to stop your depth of diaphragm wall. This is what you have to decide, not based on the earth pressure theories, etc. Earth pressure is acting only up to your depth of cut. But beyond that, what is this depth required for stability? All these things should come from the stability criteria of bottom heave and many other, which I am going to discuss soon. So this failure zone will essentially go through like this if you have a hard stratum below this layer. So it cannot penetrate through that. So it will go like this. And this portion you can easily consider as equivalent to a bearing capacity theory. And this is the failure zone. So how the stability criteria is ensured? Stability factor S needs to be calculated in such case, gamma H by Cu, and C is the weighted average, gamma is also a weighted average. Now if S is less than 6, then we call it as stable, where NC is as 6, that is, you take care in the clay soil, the net ultimate bearing capacity is nothing but QNU should be CNC, that we know for the clay soil, pure clay soil. Suppose if it is resting at the clay soil, you know what is the bearing capacity you are getting from here. So that you make use of it, and if you take this as 6, you can use S less than 6 as stable, but greater than 6 is unstable and equal to 6 will give limiting condition. So how we compute the factor of safety against this kind of stability against bottom heave? So this is the way we should calculate. So numerator should give us the resisting force against bottom heave, and the denominator should give us the disturbing force or the force which is causing bottom heave. Now let us see which force is causing the bottom heave to occur in such case. It is nothing but this portion of the soil which is producing that surcharge or the pressure, and because of which this soil is coming up. So how much is this length? Is nothing but gamma times this H, that is excavated depth. Then you have this D2 up to this layer 2, and then you have this DF up to the end of your diaphragm wall depth. So that gives you the disturbing force or total surcharge which is pushing the soil to come out from this side. Now who is resisting? So what are the resisting? Resisting force is nothing but how bearing capacity of this soil we have. So for bearing capacity we have to take the capacity at the layer 3, because this diaphragm wall is resting or ending at layer 3, not other layer. So that's why Cu3 times NC, bearing capacity factor with respect to cohesion, which should take, plus this side surcharge. You can see this side some soil is there above this, which is also stopping this upheave to occur. So this gamma 2 times D2 plus gamma 3 times DF, that also is giving you some resisting force or putting the balance. And what is this one? This is nothing but whatever interface cohesional force you are getting from here. What you get, that Cu times this H is the frictional force you are getting, plus D2 plus DF divided by your influence zone of D. Now how this D distance is calculated? This D distance should be either D1. D1 is nothing but from the end point of diaphragm wall, wherever is your hard stratum is coming, or B by root 2 typically we take. B is nothing but this distance. B can be considered equal to your width of this cut, that is braced excavated portion, because accordingly you can say this is the influence zone and that much soil is coming up. So B by root 2, among these two, whichever is smaller, whichever is lower value, that value should be considered here as the distance D, that is influence zone, to provide the friction, and that friction also resisting this soil to move downward, and that is why it is coming in the numerator. And how much factor of safety we should provide? A factor of safety of minimum 2 we should provide to avoid the bottom heave type of failure. Next stability we should consider for this kind of braced excavation is known as clay bursting. What is clay bursting? Clay bursting is nothing but, suppose you have an excavated pit in a clay layer altogether, and beyond certain depth you have a sandy layer which is more permeable than clay layer, and suppose you have a water table very close to ground surface here. So obviously this place there will be uplift pressure coming from the sand side, and clay being mostly impermeable, water is not seeping through here. But once you take out the weight from here, once you excavate out, the whatever surcharge it was earlier keeping the entire system in equilibrium, that gets disturbed. And as you have released this vertical pressure from here, this upward thrust, it may happen that upward water pressure becomes higher than this balanced thrust what was acting earlier, and then this portion of the clay will burst out or move out, fail out, and totally that water will gush through this portion, and that failure is called as clay bursting failure. So that clay bursting failure, how we consider the safety against clay bursting failure, let us look at that. So for clay bursting, as I said, this portion below the excavated part will be the cause for failure. Above the sandy layer or the permeable layer, suppose water table is standing somewhere here. So water pressure at this depth is nothing but this HW times gamma W is the upward water pressure, and what is the balancing force here? Whatever weight we are getting and whatever frictional force we are getting. So factor of safety, if we want to find out against this type of failure of clay bursting, we can write down this gamma times this depth H plus 2 times both the sides Cu into H divided by this distance of B. That is nothing but our resisting force, which resists the burst to occur or clay to come out from here. But the disturbing force is nothing but this water pressure, which is gamma W times HW. And this factor of safety for stability of design has to be more than 1.3. So if it is maintained more than equals to 1.3, then we say that clay bursting failure will not occur. Now another condition which is known as piping failure in the case of excavation in sand. Earlier one we have seen braced excavation in clay soil. Now if the braced excavation has taken place in the sandy layer, there can be two conditions. One is the sand layer extends up to an infinite depth. Another case can be sand layer extends up to a finite depth. After that you have a hard stratum. It can be a rock. It can be a very stiff clay, the impermeable, like that. So in such case, what criteria we have to check? We have to check the conventional, that piping failure criteria. That means factor of safety we have to find out in terms of hydraulic gradient I by critical hydraulic gradient IC. And here also piping failure criteria has to be satisfied with factor of safety more than equals to 1.3. You can see some design charts over there. That is for factor of safety of 1.5, factor of safety of 2, how much D by H depth is required for a given dimension of your excavated cut of width B and height H. In case of loose sand and in case of dense sand, what are the values of that? D by H needs to be provided for stability. So you get these values of embedment depth of diaphragm wall for this braced excavation. One thing is either from this clay bursting or piping failure, any one of the condition will exist at site, and braced and bottom heave criteria. Another types of failure which may occur is called yielding of the support. How the yielding of support will take place? Because due to the earth pressure in the excavated pit, this compressive stress are generated, so this strut may get yield or fail. So this struts has to be designed properly with those compressive load taken care or calculated properly. Another criteria of failure needs to be checked is excessive ground movement. Why this excessive ground movement will occur? Because you have taken out the soil from this braced excavation portion, and because of that balance of the pressure, the surrounding soil also will try to deflect. So if you see at the picture, Peck has nicely given that as this is the face of the braced excavation, and if you go away from that braced excavation zone, obviously your zone of influence of ground deflection, because some soil is coming up here and because of the bottom heave, etc. So this portion of the volume of the soil will compensate that, and this area will have some kind of depression or deflection or settlement. So if you have existing structure at this location close vicinity to this, you have a problem because of that. And you have to find out what is that influence zone for such kind of braced excavation and what is the maximum displacement can occur at different distances and also at the face of the diaphragm wall depending on what type of soil you have. So this is the Peck chart. Peck has given that zone 1 is nothing but if you have a sandy and hard type of clay, then you can consider that extent of influence zone of this diaphragm wall excavation or braced excavation is about 2 times of the depth of the excavation, and maximum displacement of the ground can occur about 1% of the height of the excavation. Whereas for zone 2 type of soil, that is which is soft clay, which is up to a limited depth of excavation, there it is 2% of maximum settlement can occur at the interface of the diaphragm wall and the surrounding soil, and the zone of influence or extent of that zone can be maximum up to this 3 times, whereas the zone 3 it can be maximum deflection of 3% over here and it can extend about up to 4 times. Considering this, one can design the diaphragm wall system. We will quickly see one example solution for diaphragm wall. Now let us go back to a solved problem which I am going to show you, and I will upload various other solved problems also on different topics, but for the timing I will show you because of the time available with us for this lecture. Can we go to the towards end? Can you type here 17? Yeah. So we will see an example problem for the case of, I have given for each topic one example problem over here. You will get it later. You can download it from this course pack. Now this is the problem which I want to discuss in detail to understand this braced excavation system very clearly, because this is very useful for any kind of underground construction, metro construction, tunnel construction, pipeline construction underground, any other underground construction. So suppose a problem set is given that braced excavation which is having a vertical cut deep of 10 meter and width of 8 meter is proposed at a clay strata, and various strata of the clay layers are given over here. Here found clay up to a depth of 3 meter, then up to 13 meter depth soft clay, and from 13 to 16 meter a stiff clay, and beyond that you have a very good dense sand with n value greater than 40. And water table exists at this depth only, that is at the interface of found clay and soft clay. Here it is mentioned that let us provide the struts at an interval of 3 meter to each other. So from the ground, so the first strut is provided around 2 meter depth. Typically we generally provide about 1 to 2 meter depth. Within that, first strut has to be provided so that maximum deflection at this portion near to the ground can be avoided. Then second strut at 3 meter, another strut at 3 meter has been provided over here. Now if we see that how to design this braced excavation system, we have to design the diaphragm wall, strut, runner beam or well, and also we have to find out the depth of the diaphragm wall. The first thing we have to find out is the depth of the diaphragm wall, otherwise we don't know how it is going to get designed. So for depth of the diaphragm wall, as I said, we have to find out the stability criteria from bottom heave and clay bursting. So first let us check for the bottom heave criteria. So in this problem you can see typically how we start with solving such problem. We generally take whatever is the depth of your excavation, that is 10 meter here h, we take another 50% extra inside the embedment as the embedment, and that's why with that 50% extra you can see over here this is about 15 meter it comes. So first assumption it is considered, let us say 14 meter is the total depth of diaphragm wall or total length of the diaphragm wall. So look at this picture, that means this is 10 meter and this is another 4 meter. Among this 4 meter we have 3 meter over here and 1 meter in the stiff clay. Because it is a stiff clay, you have to make use of this bearing capacity of this better stiff clay layer, and that's why it is extended up to that layer. Those criteria also needs to be checked. And we can consider or calculate the value of NC, that is bearing capacity due to cohesion, at that layer, that is layer 3. And you can use Kempton's equation because it is a clay layer, and let us say the value comes about 7, and B is the width of your erection is 8, and D2 value is 2 meter. Now minimum of these two you have to take, either of D2 and B by root 2, as I said, among these two, that 2 meter is coming as the minimum value. So factor of safety against bottom comes out to be that NC times Cu3 in the third layer, then gamma 2 times your df minus 1 in the second layer, and gamma 3 times 1 meter, that is your third layer. And this is the frictional component that is coming from all layers of the clay, that means from this layer, and from this layer and this one. So that's why it is mentioned over here, Cu1 times 3 meter, Cu2 times 10 meter, Cu3 times 1 meter divided by that influence distance of D1, which has been computed as minimum of these two value. And what is the disturbing force for bottom heave? It is nothing but gamma 1 times that 3 meter, gamma 2 times 10 meter, and gamma 3 times 1 meter. Let us look back. So this is the disturbing force over here, causes the bottom heave to take place. So factor of safety, by using this principle, we get about 2.8, which is greater than 2. So hence it is safe, we can say, in terms of bottom heave, if we consider that 14 meter as the total length of diaphragm wall. Next check is for clay bursting. In this case, what type of possible failure can occur? If water table is here, we have seen where the water table is here, and all are clay layers. So possibility of failure from the bottom is another possibility is clay bursting, because you have a sandy layer over here. But if these things are sandy layer, then in that case piping failure should have been checked. Now in this case, clay bursting needs to be checked, and for that the disturbing force is nothing but whatever water pressure we have. How much water pressure is acting over here? You can see this is the up to the sand layer we have to take, that 16 meter, and here 3 meter. So essentially the 13 meter column of water, how much pressure it is giving from the bottom, that we have to take, and this is the stabilizing force, whatever weight is acting in this zone, and the frictional component. So let us see what those values are coming over here. So gamma 2 times that 3 meter, gamma 3 times that 1 plus 2 meter below that, and that frictional component coming from both the sides. So 2 times of Cu of that 3 meter and Cu 3 times of the 3 meter divided by width of your cut, that is 8 meter, and disturbing force, as I said, 10, gamma W is considered 10 kilonewton per meter cube, and HW, that is column of your water standing column, is 13 meter. So with this we get the factor of safety as 1.321, which is greater than our required value of 1.3, hence it can be considered safe against clay bursting also. Now we have to check the excessive ground movement, how much excessive ground movement we should see here. You can see among those 10 meter excavated depth, most of the portions are in the soft clay layer, about 7 meter, and we can consider then it is in the zone 2 as per the PEX chart, that is soft clay within a limited depth of excavation. So maximum delta possible at the face of this wall is nothing but 2% of H. H is now 10 meter, so 0.2 meter can occur at the face. So check for this excessive ground movement. We have to check if you have an existing structure very close to that planned or proposed excavated ground, at what distance it occurs, and because of that, if maximum value is 200 mm over here, at that distance how much deflection is coming, that additional deflection you have to check with the existing structure whether it can be allowed or not. Otherwise you have to take protective measure for the structure. Now how to calculate the strut load? For the strut load we have to take the apparent earth pressure distribution given by PEC. For the apparent earth distribution calculation, you have to check first which criteria, that gamma H by Cu, whether greater than 4 or less than 4 is coming. In this case greater than 4 is coming. So accordingly you can take always that average gamma and average Cu as we have mentioned earlier, and correspondingly you can find out what is the apparent earth pressure intensity over here, this one. Once you find out the apparent earth pressure intensity and their distances, how this distribution occurs, then you know, or you have planned already at what location you are going to put your strat. So this is 3 strat P1, P2, P3 at different distances. Now we have to find out what is the influence zone for each of these strat. So for strat P1, this green color up to green color, this one gives the influence zone for strat P1. For strat P2, this is the influence zone. For strat P3, this is the influence zone. And accordingly, one can find out from this load distribution diagram how much load the strat has to carry. And depending on your horizontal spacing of the these strats, we can assume that horizontal spacing of 3 meter will be given. Accordingly, these are the 3 strat load, and among those 3 strat load, whichever is maximum, obviously you can simply design for that and put the strats accordingly. And next, the diaphragm wall, how it can be designed. The diaphragm wall, as we have already seen, the maximum bending moment we have to find out from this apparent earth pressure diagram. You know what is the maximum intensity over here, and this distance already we have provided 3 meter. So that 62 into 3 square divided by 10, that kilonewton meter per meter length is the maximum bending moment which is coming on the diaphragm wall. So you can design the diaphragm wall cross section accordingly. And how much is moment coming on the runner beam or wells? These are the runner beam at a horizontal spacing of again 3 meter, and this is the total load which is acting. You can see from here how much moment is coming on the runner beam, and accordingly you can design these wells also. So with this, we have come to the end of this course. Now I will have some interaction session with all of you. So whatever questions, queries, etc. you have, you can ask. Otherwise, anyway, you will get all the slides, then assignment problem, quiz problem, and some solved problem also on the various topics which I tried to cover through this course of 6 hours duration. Thank you.